Now here the question is, show that the sequence under root 2, under root 2 root 2, under root 2 root 2 root 2 converges and find its limit. Now for this question, a1 is 2 to the power 1 by 2, a2 is 2 to the power 1 by 2 plus 1 by 4, a3 is 2 to the power 1 by 2 plus 1 by 4 plus 1 by 8, that is an is 2 to the power 1 by 2 plus 1 by 2 square up to 1 by 2 to the power of n. Now this power is nothing but a GP, so we can write 2 to the power 1 by 2, 1 minus 1 upon 2 to the power n upon 1 minus 1 by 2. This 1 by 2 will cancel, so we'll get this as 2 to the power 1 minus 1 upon 2 to the power n, and it will always be less than 2. So we can write this an, it is greater than 0 but less than 2, that is the sequence is a bounded sequence. Now we will prove that the sequence is a monotonic sequence. Now we know that 2 to the power n, it is less than 2 to the power of n plus 1 minus 1 upon 2 to the power n, it will be less than minus 1 upon 2 to the power of n plus 1, and we can write 2 to the power of 1 minus 1 upon 2 to the power n, it will be less than 2 to the power 1 minus 1 upon 2 to the power of n plus 1. That means an will be less than an plus 1, that is the sequence is monotonic increasing sequence. Now since the sequence is bounded and monotonic, then from monotone convergence theorem we can say that the sequence converges and we need to find its limit. Now we'll take this limit n tends to infinite. If we take this limit n tends to infinite, it will be an infinite GP. Then this value will be 2 to the power a upon 1 minus r, and there will be simply 2. So this sequence, it converges to 2. So its limit will be simply 2. Now another method to solve the same question is using recursive relation. Now here a1 is root 2 and an plus 1 is root 2 into an. Now in the first part, we'll prove that this sequence is a bounded sequence and our assertion is an is less than 2. So that's your Pn. Now we'll prove the result for n equals 1. So we'll write a1 and a1 is root 2 and root 2 is less than 2. That means it is true for n equals 1. Now we'll let pk be true. It means that ak, it will be less than 2. Now we'll multiply ak with 2. So we'll write 2ak, it will be less than 4. Then under root of 2ak, it will be less than 2, and root 2ak, it is nothing but ak plus 1. So from here we can say ak plus 1 is less than 2. That means pk plus 1 is true. So from induction we can say that this an is less than 2, or this an is greater than 0 but less than 2, that is the sequence is a bounded sequence. Now for the second part, we'll prove that the sequence is monotone increasing sequence, that is an, it will be less than an plus 1. So that's your assertion Pn. We'll prove this assertion for n equals 1. So for n equals 1, we'll get a1, and a1 is root 2, which is less than under root of 2 root 2, which is a2. That is a1 is less than a2. That means it is true for n equals 1. Now for the second part, we let pk be true. So if pk is true, then ak will be less than ak plus 1. Now we'll multiply it with 2 and we'll take under root sign. So we'll write under root 2 ak will be less than under root 2 ak plus 1. Now this is nothing but ak plus 1 and this is a k plus 2. So from here we can say p k plus 1 is true. So from mathematical induction we can say that an will be less than an plus 1 and that the sequence is monotonic increasing sequence. Now, since we have proved that the sequence is bounded and monotonic, then from monotone convergence theorem, we can say that this sequence is a convergent sequence. Now we need to find its limit. So using this recursive relation, we'll take limit n tends to infinite. And if the sequence converges to some limit L, we can write L equals under root 2L. That is, the value of L is simply 2. So the sequence, it converges to 2. So that's our second method of solving this question.